Good day, viewers. We are welcome to yet another class of our online physics review. And today we are going to be talking about the topic thermal expansion. There are materials that when we heat them, they increase in length, they increase in size. Those materials we can refer to those materials as materials that have undergone expansion with heat. If I ask you to list the effect of it, we all understand that there are so many things that it can cause on an object. Most importantly, it can increase the temperature of an object, it can cause a change in state of an object, and it can also cause what we call thermionic emission. It can cause change in physical and chemical properties of the substance. But one very important thing that we know that it can also cause is that for most material, it can cause expansion. That means it can make the size of the material to increase. When we talk about the size of the material, there are three aspects to which the size of a material can be referred to. Number one, the material will have a length. Number two, it will have an area. And number two, it can have a volume. So whenever you heat materials, they increase in length, they can also increase in area, and they can increase in volume. What we are going to be studying in this topic will include the expansion and the effect of expansion on length, on area, and volume. So let us kick right into it. If we have a material whose length is given as L1, of course, that material will also be expected to be at a temperature. Okay, don't let me use 1, let me use I. If the material has a length Li, signifying the initial length, it will also do that at a particular temperature. Let me call that theta I, that is the initial temperature. When we heat this material, we expect the material to increase in length. We expect the material to increase in length, thereby having a new length that I can refer to as Lf at a new temperature, theta F. Now, the effect of increase in length that the heat will bring to this material depends on the nature of the material. That is why I can tell you that materials do not expand alike. While some expands by a greater amount than the other, some expands by a smaller amount than the other. So there is a quantity that we can use to determine the extent of expansion across different material. The quantity is called the linear expansivity. The linear expansivity. Another name for linear expansivity is the coefficient of linear expansion. It is usually represented with the Greek letter alpha, and I am going to define the linear expansivity of a substance as the change in length of that substance per unit length per degree rise in temperature. I'm going to define the linear expansivity of a substance as the change in length of that substance per unit length per degree rise in temperature. If I write that out, we understand that the initial length of this material is Li, and the final length of this material is Lf. We also understand that its initial temperature, that's the temperature before heating, or the temperature at which the length is Li. That temperature is theta I, while the temperature after heating is theta F. I can be asked to find the change in length. The change in the length of this material will be obtained by just simply subtracting the original length from the final length. That will be Lf minus Li. I can also be asked to find the change in temperature of this material. The change in temperature of this material must also be theta F minus theta I. So if I have the change in length and the change in temperature, I can simply express the linear expansivity as the change in the length, that is Lf minus Li, all over the original length, that is Li, multiplied by the change in temperature, theta F minus theta I. So to get the linear expansivity of a material, all I need to do is just to ensure that I have the change in length, I have the original length, and I have the change in temperature. When you check through the total number of quantities that I've used to get the linear expansivity of that material, there are just 4. Final length, initial length, final temperature, initial temperature. And that should give me the linear expansivity of the material. The unit for the linear expansivity of a material is the change in length is also a length value. So its unit is expected to be in meters or any other unit of length. The original length will also be in meters, while the change in temperature is expected to be in Kelvin or degrees Celsius. If I cancel out this, I will have 1 all over K as my unit for linear expansivity, and that can simply be expressed as per Kelvin. That can simply be expressed as per Kelvin. The linear expansivity of a material is a property of that material. That means if I can find the linear expansivity of a material, for example, like copper, its linear expansivity is constant. So anywhere I have copper, the linear expansivity that I have is due to be a constant value. So linear expansivity of a substance is determined by just doing the change in length all over the original length multiplied by the change in temperature. What is the significance of linear expansivity? Linear expansivity tells us how a unit length of that material will increase if I can take it through a change in temperature of 1. For example, if we are told that the linear expansivity of a material is 0.002 per Kelvin, listen to the definition of linear expansivity so that we know how to interpret this value. Because oftentimes in some examination, they can ask us not really to define linear expansivity, but they can just give us linear expansivity value and ask us to interpret what it means for a material to have those type of values. Linear expansivity of a material is the change in the length. It is the change in the length of that material per unit length of the material. When the length of that material is 1, per degree rise in temperature. Per means when you have increased the temperature by 1. So if the linear expansivity of a material is 0.002, what it simply means is this material will undergo a change in length of 0.02 meters if I can heat 1 meter of its length through a temperature difference of 1 Kelvin. I hope you understand that this delta value means the change in the length, and this delta value also means the change in temperature. So when you are told that the linear expansivity of a material is 0.002, it simply means that if you take 1 meter of that material and you heat it through 1 Kelvin, of course, there are so many ways by which you can heat it through 1 Kelvin. If its temperature is 20 and you increase it to 21, in that case, you have heated it through 1 Kelvin. If the temperature is 50 and you are heating it to 51, then you have also heated it to 1 Kelvin. So if you take 1 meter length of that material, that is what we refer to in that definition as the unit length, and you increase its temperature also by a unit, that means by 1 Kelvin or 1 degree Celsius, what you are going to have as a change in length is what we express as the linear expansivity. So if the linear expansivity of a material is 0.02 per Kelvin, it simply means that 1 meter of that material will undergo a change in length of 0.002 meters if the temperature is increased or if the material is heated through 1 Kelvin. So the significance of linear expansivity is for you to know that it is basically the change in length that will occur with a unit length of that material when you increase its temperature by 1 Kelvin. So if you give me any 3 quantities in this expression, any 4 quantities in this expression, I can find the linear expansivity. If you give me the final length, the initial length, the final temperature, and the initial temperature, I can easily find the linear expansivity alpha. If you give me alpha with any other 3 on this side, I can also simply find the 4th one. So this is the formula for linear expansivity. Meanwhile, we must also know that the material cannot just only increase in length. The material can increase in area. There are some materials that, due to their shape and size, it is more appropriate that we refer to them in terms of area and not in terms of length. Such materials are materials that have a plane shape, that we can use to refer to them. For example, if I have a metallic plate and I have a circular object, or I have a metal cut into a triangle, I cannot just be talking about the change in length for this material because they have more than length. For example, this rectangle has more than length, it has a breadth. If I eat this material, I will expect that you will know that the length will increase and the breadth will also increase, giving rise to a material with a larger area. If I increase the temperature of this material by heating it, I expect you to know that it will increase while maintaining that circular shape. The same thing will happen to our rectangle. It's going to increase in size across all its 3 dimensions, all its 2 dimensions. So then we can also be talking about the fact that the area has increased. So when you have a flat shape object, a plane shape object that is being heated, it is more appropriate that we refer to something that can help us describe its area and not just its length. That gives rise to another quantity that has to do with expansivity. This time I'll be talking about the area or superficial expansivity. So when we talk about a flat shape object for which the area can be determined, it is better that we refer to the areal expansivity instead of just its linear expansivity. If the linear expansivity is described as the change in length or the increase in length per unit length per degree rise in temperature, the areal expansivity will be similarly referred to as the change in the area per unit area per degree rise in temperature. We will see from all of these shapes that I've given to you that before eating, there's a particular area that those shapes had before. Now that you have been able to eat them, we expect you to know that it will have a final area which is expected to be more than the initial area. It will have an initial area at an initial temperature. It will also have a final area at a final temperature. It will have an initial area at an initial temperature and will have a final area at a new temperature. And the same thing for the rectangle. It will have an initial area at the initial temperature. It will have a final area at a final temperature. So with that, we can now determine the areal expansivity. The areal expansivity is represented this time with beta. The linear expansivity was represented earlier with alpha. Now we are representing the areal expansivity with beta. Another name for areal expansivity, superficial expansivity. It can also be referred to as the coefficient of areal expansion or the coefficient of superficial expansion. Both are still correct. So here, I can be asked to find the change in area. I will need to get the change in area. The change in area is definitely the final area minus the initial area, while the change in temperature is the initial temperature, the final temperature minus the initial temperature. If I bring that into this expression using my definition of areal expansion, I will have the change in area or the increase in area, in that case the final area minus the initial area, per unit area. Per unit area is per unit area multiplied by the change in temperature, theta F minus theta I. A more compressed form to write this will be change in area, which I've already expressed as AF minus AI, all over the original area AI multiplied by the change in temperature theta delta theta. So you can use this to determine the areal expansivity of a substance. The areal expansivity of a substance is also like linear expansivity, constant for that particular substance. That means if you have determined the areal expansivity of that material, Wherever you get to see that material, you can use the same value to calculate whatever parameter they want you to get about it. Areal expansivity also has a unit. We expect the unit of the change in area to be meter squared. We expect the unit of this area to also be meter squared. And we expect the unit of the change in temperature to be Kelvin or degrees Celsius. If we cancel out this item, we are going to have 1 all over K, and that is K per 1. Mind you, I've been using Kelvin, but you can also use degrees Celsius. And when you are using, if your change in temperature has already been calculated in Kelvin, that will also be your change in temperature in degrees Celsius. Anywhere in physics where you refer to change in temperature, the value you are going to get will be the same thing in Celsius as it is in Kelvin. I'll repeat that. Change in temperature values are always the same for both Kelvin and degrees Celsius. Yes, Celsius and Kelvin are not the same. Celsius, anytime we want to get Kelvin from Celsius, we know that we have to add a constant 273 to it. But that is the temperature. If we are referring to the change, anywhere we see change in temperature, the change in temperature in Kelvin and the change in temperature in Celsius are still just the same thing. Temperature is not exactly the same as change in temperature, and there are so many instances in physics that we use change in temperature. For example, when finding expansivity, we don't use the exact temperature value, we use the change in temperature value. To show you that change in temperature in Kelvin and Celsius are the same thing, I want to take two different temperature values. Let me talk about theta 1 and theta 2. Let us assume that theta 1 is 100 degrees Celsius and theta 2 is 0 degrees Celsius. If I find the change of the two temperatures, I should have 100. So that is degrees Celsius. If I decide to take them to Kelvin before finding the change in the temperature, if I take 100 degrees Celsius to Kelvin, I will have 373 Kelvin. If I take 0 degrees to Kelvin, I will have 273. If I subtract them, I should have 100 Kelvin. Showing us that while temperature values in Celsius and Kelvin are not numerically the same, by the time we find their change, we should get the same thing. So in all aspects in physics where we use change in temperature, you can work in degrees Celsius, you can also work in Kelvin, and it will still give you the same answer. Please do not confuse that with other aspects in physics where it is temperature that we use and not change in temperature. One very good aspect is the gas law. In gas law, the temperature that is in gas law is not change in temperature, it's the actual absolute temperature values. So those ones must specifically be in Kelvin. But under expansivity, where we use change in temperature, and even under the determination of it using MC change in theta, we are still going to get there, we use change in temperature. And if that is the case, you can work in both Kelvin and Celsius, and you can express your answer in both Kelvin and Celsius, and they will still be in the same numeric value. Another thing that I wish to tell you about areal expansivity is that most of the time when we solve questions about area, we are not directly given the coefficient of areal expansivity beta. Most of the time we'll be solving questions on areal expansivity, and instead they will give us linear expansivity. If I give you a rectangular plate, you will definitely know that being a rectangle, it must have an area. So I'm going to go down through the method of finding the areal expansivity to determine whatever it is they want me to find. But if I am now solving anything under areal expansivity, I expect that if a constant is going to be given, it must be the coefficient of areal expansivity. If while now solving question on areal expansion, they decide to give you linear expansivity, please understand that the coefficient of areal expansion is 2 multiplied by the coefficient of linear expansion. The coefficient of areal expansion is 2 multiplied by the coefficient of linear expansion. We use linear expansion for linear expansivity problems, length. We use areal expansion for areal expansivity problem. Where you are now given linear expansivity for an area problem, you must multiply it by 2 to get the areal expansivity before you can proceed with that particular question. So now we can continue and we can talk about the volume expansivity. There are instances too, based on the shape and size of the material that we have at hand, that it is more appropriate to refer to their volume instead of area or length. If I have a cylindrical object, if I have a cubical or a cuboidal object, if I have a conical or a spherical object, this is not a circle, this is a sphere. If I'm given any of these, or even much more that we mathematically refer to as solid shapes, then it is more appropriate that I refer to their volume and not their length or their area. It is not only their length that will expand here. I expect you to also know that they have more than a length in dimension. For example, the diameter is a length, the height is a length. If this material is heated, it will expand both in diameter and in height, leading to an increase in its volume. So it is now necessary that I decide to talk about its volume expansion. It is now necessary that I decide to talk about its volume expansion or its volume expansivity. So it means that initially I expected to have an initial volume Vi. Now, after heating, I expected to have a final volume Vf. It will have an initial volume Vi, it will have a final volume Vf. And so will be the case for the other solid shapes that we have. So now we'll talk about the volume expansivity. The volume expansivity can also be called the cubic expansivity. Can also be referred to as the coefficient of cubic expansivity. It is represented with the Greek letter gamma. The coefficient of cubic expansivity is represented with the Greek letter gamma. If linear expansivity or the coefficient of linear expansion is the change in length per unit length per degree rise in temperature, and the coefficient of areal expansivity is the change in area per unit area per degree rise in temperature, we expect the coefficient of volume expansion or the coefficient or the volume expansivity to be increase in the volume all over the original volume, the initial volume or the original volume, multiplied by the change in temperature, If that is the case, then I can simply express this as the increase in the volume. If its volume increased from V initial to V final, the increase in the volume will be Vf minus Vi all over the initial volume will be Vi multiplied by the change in temperature. The change in temperature should be theta F minus theta I. So that should be expressed as change in volume all over the original volume multiplied by the change in temperature. If we decide to get the units of cubic expansivity, we expect the unit of change in volume to be meter cube because it is a volume value. We expect the unit of initial volume to be meter cube, and we expect the unit of the change in temperature to be Kelvin. So we can now cancel out meter cube and meter cube, while the unit becomes per Kelvin. As I've said for areal and linear expansivity, you can work with degrees Celsius as your temperature, or you can work with Kelvin as your temperature, because what we are using here too is change in temperature, and you will still all get the same answer. There are instances where, like I said, for areal expansivity, you'll be solving question on volume expansivity of a material, and you will not be given the cubic expansivity. If you are not given cubic expansivity and you are given the linear expansivity, it is also very simple. Note that I said for areal expansivity, the areal expansivity is 2 times the linear expansivity. It means the cubic expansivity will also be 3 multiplied by the linear expansivity. So if you are given linear expansivity within a volume problem, you must multiply it by 3 so that you get the coefficient of volume expansivity or the coefficient of volume expansion or the volume expansivity before you can now proceed with the question. There can be instances where for a volume expansion problem, we are given the areal expansivity. If you are given the areal expansivity, you will come to this formula. You use that area to get the linear expansivity. Then you can put the linear expansivity here to get the cubic expansivity. And with that, you should be able to get whatever it is that you need. So basically, that is all for volume, area, and linear expansivity. We are now going to try to see if we can take 1 or 2 problems or examples to simplify the concept that we have been talking about. Now, some questions. We are told here that the fourth bridge has a steel span of 1,000 meters between the main piers. It has a steel span, of length 1,000 meters between the piers. Now, we are asked to calculate in centimeters. That means our answer must be in centimeters. We are asked to calculate in centimeters the change in the length of the span when the temperature changes from -10 to 30 degrees Celsius. The temperature this time is changing from an initial value of -10 degrees Celsius to 30 degrees Celsius. I'll go over the question again. We are told that the fourth bridge has a steel span of 1,000 meters between the main piers. Calculate in centimeters the change in the length of the span when the temperature changes from -10 to 30 degrees Celsius. For this question, we are given the linear expansivity of steel to be 0.000012. The linear expansivity of steel is given to be 0.000012 per Kelvin. Values of linear expansivity are actually very small. But as small as they are, when we get to the applications and consequences of expansion, we are going to see that they can actually cause very grave effects. Now, I am going to take the length given to be Li because that's the original length of that material. I want to now find the change in length. To do that, all I need to do is to express my linear expansivity. I will express my linear expansivity as the change in length all over the original length multiplied by the change in temperature. If that is the case, this is the change in length that this question wants me to find, the increase in the length. The change in length, if I make it the subject of the formula by cross multiplying, I will have the linear expansivity multiplied by the original length multiplied by the change in temperature. The linear expansivity for this question is 0.000 another 0.12 multiplied by the original length of that material is 1,000, while the change in temperature of the material is the final length. The temperature has been heated from -10 initial to 30 degrees Celsius final. So that would be 30 degrees minus -10. If we do that, we should have what is equal to 0.000012 times 1,000. That should give us 0.000012 multiplied by 1,000. And the brackets here I have 30 minus is plus. Why do we even have two negatives? There's a negative that comes with the change that we are looking for, and the item that we are also subtracting has a negative. So we must ensure that we put the two. One cannot stand in place of the other. So if we do this, 0.00012 times 1,000 should be 0.012 multiplied by 30 plus 10 is 40. If we do that, we should have 0.48 meters. But mind you, we are asked to get our answer in centimeters. I'll take that meters to centimeters and it will become it will become multiplied, it will be multiplied by 100, and that should give me 48 centimeters. And that is the value that we have for this. We can move on. There's another question that we can take that I expect us to take. Now, we are told that a square plate, it is necessary that we know that now we're talking about a plate, and plate is one of the items that I said it is more appropriate to refer to considering the area. Now, a square plate of side 10 centimeter, the side of that plate is 10 centimeter, but mind you, it is a square. Now, a square plate of side 10 centimeters is made up of a metal of linear expansivity 2 times 10 raised to power minus 5 per Kelvin. The linear expansivity of the material that has been used to make this plate is 2.0 times 10 raised to power minus 5 per Kelvin. We are also told that as the plate is heated from 30 degrees Celsius to 100 degrees Celsius, what will be the area of one face of the plate? What will be the area as it is heated from 30 degrees to 100 degrees? It is heated from an initial temperature of 30 degrees Celsius to a final temperature of 100 degrees Celsius. So what will be the final area? So even if we don't know that this question is an area problem, the item that we are asked, the parameter that we are asked to determine is an area. So we have to solve it considering the areal expansivity. Now, there are times that we may not even know, the question may not come that direct, but we're expected to understand that the square will expand both in its length and in the other length, so it will expand in its area. So we have to solve it. Once a plain mathematical shape is given, we have to solve it as an area problem. Once a solid mathematical shape is given, like cube, cuboid, cone, sphere, or cylinder, then we have to solve it like a volume question. We are still going to get to something like that. But for an area problem, we don't need the linear expansivity, or linear expansivity is not what we are going to use. Though it can give us what we need, what we are expected to use for solving area is the areal expansivity. We use linear expansivity to solve length problem. We use areal expansivity to solve area problem, and we use cubic or volume expansivity to solve volume problem. So we can easily write out the formula that areal expansivity is the change in area all over the original area multiplied by the change in temperature. So there are two things we are going to find before we can proceed. The very first thing is we need to know the initial area. That should not be difficult considering the fact that it is a square and we are given the length. The area of a square should be the length squared, and that should be, the length is 10 centimeters. If you square 10 centimeters, you are expected to have 100 centimeters squared. So that is the initial area for a square of side 10 centimeter. Now, one other thing that we can find is we are not given the coefficient of areal expansion, but we are given the coefficient of linear expansion. I told you earlier that we can actually solve one from the other. The coefficient of areal expansion is always 2 times the coefficient of linear expansion. That should be 2 multiplied by the coefficient of linear expansion is 2.0 multiplied by 10 raised to power minus 5. If we do that per Kelvin, we should get 4.0 times 10 raised to power minus 5 per Kelvin. And if that is the case, we can now substitute into our expression to get what is it that we need to get. So the areal expansivity is 4.0 times 10 raised to power minus 5 is equal to the change in area all over the original area. The original area here has been calculated to be 100 multiplied by the change in temperature. Change in temperature is evaluated as the final temperature 100 minus the initial temperature 30. Always do the final minus the initial. It is very important that you take it as the final minus the initial. So I can cross multiply to find the change in area. The change in area must therefore be equal to 4.0 times 10 raised to the power minus 5 multiplied by 100 multiplied by the change in temperature, which is 70. If we continue with that evaluation, we should have 4.0 multiplied by 10 raised to the power minus 5. I wish to express everything in standard form. 1 times 10 raised to the power 2, that is 100, and 7 times 10 raised to the power 1, that is 70. So we can continue. We'll multiply the numbers. 4 times 1 is 4, times 7 is 298.0. 10 raised to the power minus 5 times 10 raised to the power 2 should be 10 raised to the power minus 3. 10 raised to the power minus 3 times 1 times 10 raised to the power 1 should be 10 raised to the power minus 2. If we complete that in standard form, we should have 2.8 times 10 raised to the power minus 1, or more appropriately expressed as 0.28 centimeters squared. But that is not what we are asked to find. We are asked to find the final area. Note that the change in area is the final area minus the initial area. If that is the case, the answer is 0.28. If we cross, we'll have the final area being the initial area plus 0.28. And the original area is known to be 100. If you add the 0.28 to that, we should have 100.28 centimeters squared. And that is the answer to this question. We can continue with the solution of more problems. So we have a metal cube of side 5 centimeters and linear expansivity 2 times 10 raised to the power minus 5 per Kelvin is moved from an ice water mixture into boiling water. The increase in the volume of the cube is dash. We have a cube. The side of that cube is given to be 5 centimeters. The side of the cube is given to be 5 centimeters. That is the side of the cube. We are told that this cube, the material that is used to make the cube, has a linear expansivity of 2 times 10 raised to the power minus 5. 2 times 10 raised to the power minus 5. We are also told that this cube has been moved from an ice water mixture to boiling water. It was moved from an ice water mixture. We expect an ice water mixture to be at a temperature where ice changes to water or water changes to ice. That would be 0 degrees Celsius. So that is where it was moved from. So we take that 0 as the initial temperature. It was now moved to boiling water. It was moved to boiling water. Boiling water, water boils at 100 degrees Celsius. So we take 100 degrees Celsius as a final temperature. If that is the case, then we can now continue with the solution of the problem. But what is it that they want us to find? They said we should find the increase in the volume. The increase in the volume. So the increase in the volume will give us the hint that we should solve the question as a volume problem. Even though we are not, that is not what is required of us, we should know that since we have been given a cube, and a cube is a solid shape in mathematics, it is more appropriate that we refer to its volume when we are talking about its shape or size. So we can write the coefficient of cubic expansion. That should be change in volume all over original volume multiplied by the change in temperature. If that is the case, we can cross multiply. If we do, we should have the change in volume becoming the coefficient of cubic expansivity multiplied by the initial volume multiplied by the change in temperature. Now, before we proceed with this question, we'll discover that there are two things that we need that is not given. We need the initial volume that has not been given directly. We also need the coefficient of cubic expansivity that has also not been given. Instead of coefficient of cubic expansion, we are given the coefficient of linear expansion. We can't use coefficient of linear expansion to solve a volume problem. We have to change it to cubic expansivity. And mind you, at the start of the class, I told you that the coefficient of cubic expansion is 3 multiplied by the coefficient of linear expansion. So we should have 3 multiplied by the coefficient of linear expansion is 2 times 10 raised to the power minus 5. And that should be 6 multiplied by 10 raised to the power minus 5. And that should be the coefficient of cubic expansion that we are going to use for this problem. Another thing that we are not given in this question that we also need is the initial volume. We are not given the initial volume, but we are given the initial side, length of the side. That initial length of that side is 5 centimeters. We can now find the volume of this cube. How do we get the volume of the cube? The volume of a cube is the length cube. The volume of a cube is the length cube. That means the volume must be equal to the length itself is 5 centimeters. If we decide to find the cube of it, we'll get it as 5 cube, that is 125 centimeter cube. That will be taken as the initial volume, since what we use is the initial length. So we can easily now get the change in volume. The change in volume must be the coefficient of cubic expansion multiplied by the initial volume multiplied by the change in temperature. If we do that, we'll have the coefficient of cubic expansivity, that is 6 multiplied by 10 raised to the power minus 5, multiplied by the initial volume is 125, and multiplied by the change in temperature. The change in temperature in this case is 100 minus 0, that is the final temperature, 100 degrees Celsius, minus 0 degrees Celsius. So if we do that, we should have 6 times 10 raised to the power minus 5 multiplied by 125 multiplied by 100 that we are going to get out of that bracket. We can continue with the evaluation. We'll have 6 times 125 multiplied by, I'm bringing out those numbers that do not have 10 powers, times 10 raised to the power minus 5 multiplied by 10 raised to the power 2. If we continue with this explanation, we'll have 6 multiplied by 125 should give us 750. We'll multiply by that by 10 raised to the power minus 5 times 10 raised to the power 2 should give us 10 raised to the power minus 3. If we split it out in ordinary form, we'll have 0.750 in centimeter cube. And that will be the change in volume for this question. We can then move on. All of what we have solved thus far are expansion in solid. Why? Because it is only solids that will have length, area, and volume. Only solid objects can have length, area, and volume. Liquids do not have length and area. Nobody can find the length of water. Nobody can find the area of water. You can find the surface area of water if it is put in a container, but water itself does not have an area, so it does not have a length also. Gases do not also have length. They do not also have area, so nobody can find linear expansivity of liquids or linear expansivity of gases. Nobody can also find the areal expansivity of liquids or areal expansivity of gases, because both liquids and gases do not have area and length. So the only expansion that we can determine for liquids particularly, or even gases, are their volume expansivity. Water has volume. Liquids do have, gases too have volume. Liquids generally have volume, gases have volume, though the volume of gases depends on the prevailing temperature and pressure under which they are kept, because gases are compressible. They can have a volume of 5 centimeter cube now, but if you increase the pressure on them or you reduce the temperature, it's possible for you to compress them such that they will now have lower volume. But liquids are incompressible, so they have their own volume. Now we can determine for liquids, we can determine their volume expansivity. But for one issue that you are going to definitely have, for liquids, I need you to understand that it is impossible for you to heat liquid alone. It is impossible for you to heat liquid directly. If I need to boil water, I must put it first in a container before putting it on fire. It is not possible for you to boil water without putting it first in a container. There must be a container in which you are going to put them. The big problem with that now is the container too, under the change in temperature that you want to expose the liquid to, will also expand. Liquids cannot be heated alone. They must be heated in a container. The container in which they are going to be heated must also expand. So that means that we cannot directly study the volume expansivity of liquids alone. So there are 2 points that I've raised now. Liquids and gases do not have area and linear expansion because they do not have length and they do not have area. The liquids and gases will only have volume expansion. As said, we can study the volume expansivity of liquids. We can also study the volume expansivity of gases, but most of the time we have to take into account their prevailing pressure and temperature. And generally, that is what we do under gas law, the interdependence of volume with pressure and temperature. But for gases, for liquids, we don't really need to consider their pressure and temperature because they are incompressible. We don't need to consider their pressure, we need to consider their temperature because it's the effect of temperature on their volume that we're actually talking about here. So liquids will have a volume expansivity, only that their volume expansivity is not going to be a pure volume expansivity, or it will come in different forms. Why? Because they can only be put in a container. The problem that we create for us is that the container too will expand. So when you see the expansion of liquids inside a container, you are seeing the resultant expansion of both the liquid and the container. So because of that now, we study 2 types of expansion, volume expansion for liquids. We study what we call the real cubic expansivity of liquid, and we also study the apparent cubic expansivity of liquids. Apparent, don't forget, comes from the word appear. What it appears to be might not what it is exactly. Real is talking about what is the real expansion of that liquid, while apparent is what the liquid, the value through which the liquid appear to have expanded by. I'm going to bring up one illustration. Let us assume that it is possible for us to have a measuring cylinder. Let us assume that it is possible for us to have a measuring cylinder that is graduated in volume scale. Let's assume that this is 2 centimeter cube, 4, 6, 8, 9, 8, 10, 12, 14, 16, 18, and 20 centimeter cube. That is a container. Let us assume also that it is a transparent container like glass. If we have water, let us also assume that we have water in it up to the 14 centimeter cube mark. There's water in it up to the 14 centimeter cube mark. Now, we decide to start eating. What will happen is, yes, the liquid is going to expand, but before the expansion of that liquid, the glass will expand because the glass is closer to the source of heat, so it will experience the heat first. We expect it to expand first. When the glass expands, what it means is it's going to expand by creating more space within it. And if it's going to create more space within it, we expect the liquid to first go down to fill that additional space that has been created. So what will first occur is that the level of water in the container will first go down. It will go down not because the water has contrasted. No, the water is still the same volume, but it is a container this time that has created additional space within it. So once you create an additional space, we expect whatever you have put inside the container to reduce in volume, So it is now making it look as if it is 12 centimeters cube, 12 centimeter cube. Now, if you continue eating, of course, the heat will eventually get to the liquid inside the container, and the liquid will also now expand. And most times, expansion in liquid is a little bit more than the expansion in solids. What that means is by the time the liquid expands, by the time the liquid starts to expand, it will now expand beyond where it is expected to expand, beyond where it is or where it was. So if it now eventually gets to 18 due to the heating process that you have taken it through. Now, if we look at this example very well, if I ask you by what amount has the liquid expanded, if you are, let us assume you place this on fire or the flame, and you left to come back to meet it, you will assume that the water has expanded by 4 centimeter cube. Why? Because you left it at 14 and you came back to meet it at 18 centimeter cube. So you assume it has expanded by 4 from 14 to 18, and that is logical enough. But if you were there through the process, you will understand that the level of water first went down to 12 due to the expansion of the container. And when it was time for the water itself to expand, it did not expand from 14. Instead, it expanded from 12 to 18. So the expansion of that water is actually 6 centimeter cube, not 4 centimeter cube. So when you check very well, you will discover that technically there are 2 different types of expansion based on how you want to look at it. There's one that the container made us believe, and there's another one that is actually happening that we have to pay closer attention to before we understand that that is what is taking place. So there's a real expansion and there's an apparent expansion that is occurring to that liquid. The real expansion is the expansion that actually took place when the water started expanding, and that is the expansion from 12 to 18. So the real expansion is 6. But it appears to an unsuspecting person that the liquid has expanded from 14 to 18, because to you, you left it at 14 and you came back to meet it at 18. So to you, the liquid has expanded by only 4. So that 4 will be referred to as the apparent expansion, what the expansion that we have been made to believe. What appears to be its expansion is the apparent expansion, but the real expansion is what actually took place, and you have to be more technical to really see that. So for liquids, because liquids are usually heated in a container, we talk about 2 of the expansion, and those 2 are the apparent cubic expansivity and the real cubic expansivity. I will define the 2 of them. The real cubic expansivity of a liquid is the increase in volume per unit volume per degree rise in temperature of that liquid. The increase in volume per unit volume per degree rise in temperature of that liquid. Very simple, right? That looks very much like the cubic expansivity that we explained for solid earlier. Now, the apparent cubic expansivity of the liquid is the increase in volume per unit volume per degree rise in temperature when the liquid is heated in an expansible container. When the liquid is heated in an expansible container, the apparent cubic expansivity is telling us what will take place. What we will see if the liquid is placed in a container. The real cubic expansivity is telling us what will actually take place if it were possible for us to consider only the liquid without the container, which is the real thing that will happen to the liquid. So I will define the two so that you get to see the difference. Just a small phrase at the end of their definitions. The real cubic expansivity is the increase in volume per unit volume per degree rise in temperature of that liquid. The increase in volume per unit volume per degree rise in temperature of the liquid, while the apparent cubic expansivity is the increase in volume per unit volume per degree rise in temperature when the liquid is heated in an expansible vessel. Now, going back to our illustration. If I've asked for the change in volume of that liquid, the apparent change in volume of that liquid, we agreed from my explanation earlier that the apparent change in volume is 4 centimeters. It looked as if the liquid expanded by 4 from 14 to 18. But the real change in volume of that liquid, is from 12 to 18, which is 6 centimeter cube. 6 centimeter cube. Now we will observe that the change in volume of the container seems to be 2. I will explain. The container, the water that you put inside the container was at 14. When the container expanded, the water went down to 12. That means it looked as if the container created an additional 2 centimeter cube space within it. That is why it looks like the container became larger by 2. So the liquid level had to go down because the liquid went down to fill the additional space created by the expansion of that container. So the expansion of the container is 2 centimeter cube. This value now makes it look as if I add the change in volume of the container to the apparent change in volume, I will get the real change in volume. This is a very important formula under this concept, and that can also be extended to their cubic expansivity. It therefore means that if I can find the cubic expansivity of the container and I add it to the apparent cubic expansivity of the liquid, I will always get the real cubic expansivity of the liquid. This is for the liquid, this is for the liquid, this is for the solid container. The first formula that I would like to give you, the first important formula that I would like to give you under this concept is the cubic expansivity of the container. When you add it to the apparent cubic expansivity of the liquid, you must get the real cubic expansivity. And we are going to try to see if we can work with that. Now, I need you to understand that there are specific formulas that can be used to find the apparent cubic expansivity and the real cubic expansivity. This is the real cubic expansivity, sorry. To find the apparent cubic expansivity and the real cubic expansivity, we can use the standard formula for cubic expansivity, which is the change in volume per unit volume per degree rise in temperature. Change in volume per unit volume per degree rise in temperature. It looks like the same, it pretty look like the same formula, only for the fact that if you are looking for apparent cubic expansivity, the change in volume that you're expected to use is the apparent change in volume. If you are looking for the real cubic expansivity, the change in volume that you are looking for must be the real change in volume. For example, for the last illustration, if I want to find the apparent cubic expansivity of that liquid, I have to use the apparent change in volume. And the apparent change in volume for that should be 18 minus 14, which is 4. But if I'm looking for the real cubic expansivity, I will have to use the real change in volume. The real change in volume was 6 centimeter cube because it went from 12 centimeter cube to 18 centimeter cube. So the change in volume, the form of the change in volume that you are using will help us determine the type of cubic expansivity of that liquid that you are looking for. If it is an apparent change in volume, you are getting the apparent cubic expansivity. If it is a real change in volume, you are getting the real change in the real cubic expansivity. So note those two down as the first set of formulas that I'll be giving you for linear, for cubic, for real cubic expansivity and apparent cubic expansivity. Then we can continue from there. If we do this, we should now look for other formulas. Generally, let us consider a liquid alone. If we have to consider a liquid alone, we understand that while the volume of a liquid will change anytime it is heated, or the volume of objects generally will change anytime they are heated, the mass of the object is expected to remain the same, except there's a chemical reaction that occurs on heating. A substance mass is not expected to change upon heating. The mass should go with the law of conservation of mass or matter, which naturally states that matter can neither be created nor destroyed. It is not possible for you to create matter. It is not possible for you to destroy matter. If I'm starting a system with 5 grams of a substance, throughout the process, I must be having 5 grams of, it could be the substance or some other substances if there's a chemical reaction that is occurring. But here we are not even talking about chemical reaction. We are not even talking about thermal reactions or thermal associated reactions like thermal decomposition or thermal dissociation. We are talking about just the effect of heat on the size of an object. Anytime you heat an object, the volume will change, but the mass of that object remains the same. So if we look at this formula from the class on density that we have had, we said that the density of a substance is the mass of that substance divided by the volume. So therefore, if I heat a substance, I have already established that the volume will change due to expansion. The mass can never be affected by heat. The mass is not affected by heat. If the mass is not affected by heat, then I expect you to know that the only other thing in this formula that can change must be density. Must be density. It is not possible for you to have an equation that depends on 3 quantities. If one part of that quantity remains the same and one is changing, there must be another quantity that must change with it. For example, we know quite well that 6 is 6 divided by 1. For this to remain 6, if I have to change 1, then this answer must also change. If this must remain 6, and I decide to change this one to 3, then we expect that the quotient that we are going to have cannot be 6 anymore. It has to be 2. It means that as I have increased 1 from 1 to 3, the 6 has also reduced from 6 to 2, while the other part of the equation remains the same. So if an item in an equation that has only 3 parameters is changing and 1 is constant, then there must be another item that will change with it. Now, if due to heat, there's a change in the volume of a substance, we expect the density to also change. We expect the density to also change. So what I'm going to do here is I will try to make the mass of the substance the subject of the formula. Mass of the substance becomes the density of the substance multiplied by the volume of the substance. Now let us assume that we have heated the substance. So it is, before heating, we expect the substance to have an initial volume. After heating, we expect it to have the final volume. If we write an equation for the initial condition, the initial mass must be equal to the initial density multiplied by the initial volume, while the final mass must also be equal to the final density multiplied by the final volume. But I just told you that there is no initial mass and there is no final mass. Heat does not affect the mass of a substance. If heat does not affect the mass of a substance, then we can say that the initial mass and the final mass must be the same. If that is the case, the initial mass, which is rho I VI, must be equal to rho F VF. It simply means that if I bring the volumes to one side and the density to the other side, I should be able to have Vi all over Vf all over is equal to rho F all over rho I. If I bring rho I here and Vf here, I should be able to have this expression. So the ratio of the initial volume to the final volume must be equal to the ratio of the final density to the initial density. I am going to do something with that, and I want you to please come with me. Remember that we said that the real cubic expansivity must be change in volume should be Vf minus Vi all over Vi multiplied by the change in temperature. If we decide to cross multiply, we should have Vf minus Vi is equal to the real cubic expansivity Vi multiplied by the change in temperature. If we decide to take Vi to the other side, we'll have Vi plus rho real cubic expansivity Vi multiplied by the change in temperature. If that is the case, we'll say that Vf is equal to, if we factorize Vi out, we have 1 plus rho the real cubic expansivity multiplied by the change in temperature. If we now decide to divide both sides by Vi, if I divide both sides by Vi, I should have an expression that looks like Vf all over Vi is equal to 1 plus real cubic expansivity multiplied by change in temperature. I'm not done. We can now come here. If Vi over Vf is equal to rho F over rho I, let me do the inversion of both sides. If I do that, I expect you to know that Vf all over Vi must be equal to rho I all over rho F. So an expression that I have now just obtained for this, for Vf all over Vi, is rho I all over rho F. If I decide to substitute this for this in this equation, I will have rho I all over rho F is equal to 1 plus the real cubic expansivity multiplied by the change in temperature. If I cross multiply, I should have rho I, that's initial density, is equal to rho F multiplied by 1 plus rho the real cubic expansivity multiplied by change in temperature. If we continue to simplify that expression by using this to multiply others, we'll have plus real cubic expansivity multiplied by change in temperature multiplied by rho F. We can bring this here. That becomes initial density minus final density is equal to the real cubic expansivity multiplied by change in temperature multiplied by the final density. If we divide both sides by the change in temperature and the final density, the change in temperature and the final density, we should have an expression that looks like the real cubic expansivity is also going to be rho I minus rho F all over rho F multiplied by change in temperature. And this is another formula that we can use to find the real cubic expansivity. That is another formula that we can use to find the real cubic expansivity. I expect you to check this with that of the volume. You will see that everywhere I have used the initial volume, I seem to have replaced it with the final density. And everywhere I've used the final volume, I seem to have replaced it with the initial density. So clearly, density can also be used to determine the real cubic expansivity of a liquid. Density can also be used to determine the real cubic expansivity. It is not necessary that you get to learn this derivation the way I've given to it. It is not a commonplace that you'll be asked to derive the formula. If you can follow up with the derivation, that is good. But if you cannot follow up with the derivation, it is necessary that you know what is important. And that is just the formula for finding the real cubic expansivity. Now I've given you two different formulas that you can use to find the real cubic expansivity. You can use the change in volume all over original volume multiplied by change in temperature. You can also use the change in density, but this time the change in density will be calculated not as final minus initial. It will be calculated as initial minus final, because it is believed that anytime the volume increases, the density will drop. So we expect, therefore, that the final density must be less than the initial density. If you place the final density in front and the initial density at the back, you'll get a negative cubic expansivity. Not that cubic expansivity cannot be negative, I need to tell you. You can get cubic expansivity, linear expansivity, even areal expansivity to be negative. But you really need to know that that negative you are getting, is it a negative that should be in the answer, or negative that you are forced to be in the answer because you have not properly arrange the quantity as required. If I was talking about negative expansivity, a substance can have a negative expansivity. Negative expansivity implies that when you heat the substance, instead of expanding, it is contrasting. That's the meaning of negative expansivity. And there are few very special materials that behave like that. There are materials that upon heating, though they are very few and very scarce, upon heating, instead of them to expand, they seem to contrast. Upon heating, instead of expanding, they seem to contrast. We even have some material whose expansivity is equal to 0, or very close to 0. If a material's expansivity is 0, it simply means that heat does not have effect on the size of that material. That means when you increase the temperature of that material, the length that it has before is almost going to be the new length that it will also have. It will not increase. And there are instances, there are applications, very good applications for those type of objects or for those type of materials. If you want to design a material and you don't want it to really affect the material, then you want to design a machine, and you want the machine to be resistant to it. You want the machine to be such that it will not in any way affect it. Then you must look out for material whose expansivity is as close to 0 as possible. Now we are done with real cubic expansivity. We should talk about apparent cubic expansivity. One formula for apparent cubic expansivity is what I have given to you here. Another formula for apparent cubic expansivity is in terms of quantity of an object expelled. If I have a container that is filled with a liquid, a container that is completely filled with a liquid, then I will know the volume of the container. That also be the initial volume of the liquid. I know the initial volume of the liquid. I know the initial volume of the container. The volume of the container automatically becomes the volume of the liquid since the liquid is filling the container. I will also know their initial temperature. That's the prevailing temperature under which this condition is set. So if I decide to also find the mass of the liquid inside this container, how can I get the mass of the liquid in the container? I can get the mass of the empty container before filling it with the liquid. Let us call that mass M1. I can also find the mass of the container now filled with the liquid. Let us call that mass M2. We expect that the change between the masses, M2 minus M1, will give us the mass of the liquid inside the container alone. So if I know the mass of the liquid in the container as M, if I now decide to heat, based on what I've explained earlier, I will expect the level of the liquid to first go down because of the fact that the container will be the first to expand and create additional space within it. But ultimately, by the time the liquid starts to expand, I will expect that the liquid will not expand to cover up for that deficit that has been created by the expanding container, and it will now also overflow, because I said that liquid's expansion is more than that of the container. So if the liquid is going to expand, it will expand beyond the extent of the container. So it will leave the some part of it will overflow and drop out of the container. Of course, if this were to be a flammable liquid, then you have to be very, very careful when setting this up. It is such that you have to use what we call a water bait. The container must be closed and you must heat this inside water. So some of the liquid will escape. because it has created, the volume will be such that the container will not be able to accommodate the increase in the volume of the liquid any longer. So if that is the case now, at the end of this process, I can now find the final temperature. But one thing will have changed. Surprisingly, that thing that will have changed might not exactly be the volume. It may not be the volume. Because understand that we started with a filled container, of a container filled with liquid, and we're also ending with the same container filled with the liquid. The only thing that will have changed in this process now is the mass. The only thing that will have changed in this process is the mass inside the container. How would the mass have changed? How do you expect the mass to have changed? We expect that since some of the liquid has overflown out of the can, the mass will have reduced, even though it looks as if we still have the same liquid in the container. But some of them have overflown. Those liquids that overflew out of this container definitely have their own mass, and they have taken the mass away with them. So if we are starting with a liquid of, let's say, 10 grams, we are definitely not going to end with that same 10 grams liquid. So to do that, we'll get the mass of the liquid that has overflown out of that liquid. I'm going to call it the mass of the liquid expelled. I'll represent it with delta M, and I'll call it the mass of the liquid expelled, mass of liquid expelled. So if I know the mass of the liquid expelled, I can determine the apparent cubic expansivity from the mass. And how will I do that? I can say that the mass of the liquid expelled, if I divide it by this time the final mass, that is the mass that is left inside the container, multiplied by the change in temperature, should give me the apparent cubic expansivity. It is so easy to know that this is apparent cubic expansivity because I am finding expansivity when the liquid is inside the container. So that is the formula for another formula for apparent cubic expansivity. So now we know 5 relations between apparent and real cubic expansivity. There are 2 distinct formulas that we can use to find the real cubic expansivity. There are 2 distinct formulas that we can use to find the apparent cubic expansivity. And there is a formula that we can use to connect between the real and the apparent cubic expansivity if we know the cubic expansivity of the container. Now we take example on thermal expansion, particularly with regards to the expansion of liquid. Here we have a glass flask of volume 1000 cm cube. A glass flask whose volume is 1000 cm cube. I'll call that the initial volume. It's still just a flask, so I'll be hoping that this is a volume expansion problem. Filled with mercury. That is where it becomes a liquid problem. There's this flask. It is now filled with mercury. Mercury is a liquid. So we have been given the volume of the liquid because the liquid has filled, or the liquid is filling this container. So its initial volume will also be 1000. A glass flask of volume 1000 cm cube filled with mercury is heated from 30 degrees Celsius to 80 degrees Celsius. Is heated from an initial temperature of 30 degrees Celsius to the final temperature of 80 degrees Celsius. 80 degrees Celsius. If the cubic expansivity of glass and mercury are 2.4 times 10 raised to the power minus 4 per Kelvin and 1.8 times 10 raised to the power minus 4 per Kelvin, the cubic expansivity of glass and the cubic expansivity of mercury is 2.4 times 10 raised to the power minus 4, 2.4 times 10 raised to the power minus 4 per Kelvin, while that of mercury is given to be 1.8 times 10 raised to the power minus 4 per Kelvin. The question that they want us to solve is that we should find the apparent increase in volume of mercury. The apparent increase in volume. the apparent increase in volume. Increase in volume is the change in volume. The apparent change in volume of that mercury is what they want us to find. So that is simple enough for us to do. In solving for this, we need to look at the quantities that are given very well. This is the glass. The glass is expected to be the container. I don't have any problem with it. This is mercury, the liquid in the question. Whenever we have liquid, whenever we are given the cubic expansivity of mercury or liquids, we should probe further. The cubic expansivity, is it the apparent cubic expansivity or the real cubic expansivity? Because now we know that liquids will have two types of cubic expansivity, the real cubic expansivity and the apparent cubic expansivity. We need to know which one the question is referring to. And I must tell you, if you are given cubic expansivity, without being told if it is apparent or real, then it is the real cubic expansivity. If you are given cubic expansivity of a liquid and you are not told if it is real or apparent, then you will take it as real. If it is apparent, it must be specified. It is like a negative and a positive number. If a number is negative, the negative must be written. If a number is written without putting any sign, either positive or negative, we usually always take it as positive. Positive does not have to be indicated, but when it is negative, it must be indicated. Real is the actual expansivity of the substance. So when you are given the expansivity of the substance, you take it as the real. If it were to be the apparent, then the question will indicate such. So I'm going to call this the real cubic expansivity of the liquid. I'm going to call this the real cubic expansivity of the liquid. But the question is, what I've been asked to find is the apparent change in volume. So the very first thing I'm going to do is I will try to find the apparent cubic expansivity, because that is where the apparent change in volume will come from. Remember that I gave you this formula, that the apparent cubic expansivity of a liquid plus the cubic expansivity of the container must give us the real cubic expansivity of the liquid. So from this expression, I have enough information to find the apparent cubic expansivity of mercury. The apparent cubic expansivity will be the real cubic expansivity minus the cubic expansivity of the container. The real cubic expansivity in this case is 1.8 times 10 raised to the power minus 4 minus 2.4 times 10 raised to the power minus 4. If I subtract that, I will have 0.6 times 10 raised to the power minus 4 per Kelvin. Please don't be surprised that you have a negative in the apparent cubic expansivity. It is very possible. I was saying it earlier that substances can have negative expansivity. But this one is so special. It has a positive real cubic expansivity, but it has a negative apparent expansivity. How is that so? It means naturally, if it were possible for us to heat the mercury alone, it will expand. But inside the container, it's going to appear as if it's going to contrast. And that is because its expansion is not up to that of the container. While the container will expand in the range of 2.4, the liquid will expand in the range of 1.8. So when you put the liquid inside the container will create more space within it than the liquid will be ready to fill. So because of that, it will give you an impression that the liquid has not expanded, that instead it has even contrasted. But the real cubic expansivity is showing us. Real is what is telling us what will actually happen to that liquid. It's telling us that when you heat it, it will expand. It's only that when you put it in a container whose expansion is more than its own, it will look as if it is going to contrast. So I am going to now do the apparent. I'll write the formula for apparent cubic expansivity, the one that has the item that I am looking for. The apparent cubic expansivity will be the change in volume, apparent change in volume all over the original volume multiplied by the change in temperature. If I do that, I will have the change in volume, the apparent change in volume, to give us the apparent cubic expansivity multiplied by the initial volume multiplied by the change in temperature. The apparent cubic expansivity is minus 0.6 times 10 raised to the power minus 4 multiplied by the change in temperature. The change in temperature is 80 minus 50. If we do that, we are going to 80 minus 30, sorry. If we do that, we are going to have minus 0.6 times 10 raised to the power minus 4. Okay, we still have the initial volume of the mercury to multiply this expression by times 1000. 1000 is 10 raised to the power 3. The initial volume is given here as 1000 centimeter cube. I will now multiply it by 50, which is the change in temperature. If we bring that all together, we have minus 0.6 times 50 multiplied by the change in temperature, 10 raised to the power minus 4 times 10 raised to the power minus 3 will be 10 raised to the power minus 1. So we have minus 0.6 times 50 should give us minus 30. Minus 30 times 10 raised to the power minus 1 should give us 3 centimeter cube. And what have we been asked to find? We have been asked to find the apparent increase in volume of the mercury. The apparent increase in volume of the mercury is minus 3. Being minus, it means the volume will not even increase. Instead, the volume will reduce. We appear to have reduced by 3 because it is apparent cubic expansivity that we are looking for. We'll take more questions. A density bottle of volume 500 centimeter cube is filled with a liquid and heated from 20 degrees Celsius to 60 degrees Celsius. If 7.5 centimeter cube of liquid is expelled, what is the apparent cubic expansivity? What is the apparent cubic expansivity of that liquid? That is simple enough to get. We are told that a density bottle of volume 500 centimeter cube. The initial volume is 500 centimeter cube. It is filled with a liquid and it is heated from 20 degrees Celsius to 60 degrees Celsius. It is filled with a liquid and it is heated from 20 degrees Celsius, my initial temperature, to a final temperature of 60 degrees Celsius, 60 degrees Celsius. If 7.5 centimeter cube of liquid is expelled, the volume that is expelled must be the change in volume. The change in volume is the volume expelled and it will be 7.5 centimeter cube. 7.5 centimeter cube is the volume expelled. The apparent cubic expansivity of the liquid is what? The formula for the apparent cubic expansivity is the apparent change in volume all over the original volume multiplied by the change in temperature. Anytime you place a liquid inside a container and certain volume of that liquid has been expelled, that seems to look as if that is what we are going to use as the change in volume of that liquid, the apparent change in volume. That will be taken as the apparent change in volume, and we can now solve it as 7.5 centimeter cube. Everything that is needed is given. All over the initial volume is 500 cm cube, 500 cm cube multiplied by the change in temperature. The change in temperature will be 60 minus 20. If we do that, we are going to have 7.5 all over 500 multiplied by the difference between 60 and 20, which is 40. If we do that, we are going to have 7.5 divided by 500 divided by 40. 3.75 times 10 raised to the power minus 4. The answer is 3.75 times 10 raised to the power minus 4. That is all about that. That should be direct as possible. Now, we can also continue with another question, and this will be the last question for today. We'll have The bulb and the stem of a thermometer contain a 0.4 centimeter cube of mercury up to the 0 mark. There's a thermometer. You refer to our class on temperature and its measurement to understand what the bulb and the stem of a thermometer looks like. But for now, I can tell you that this is the stem, this is the bulb, and here is the stem. The stem is actually the narrow pathway through which the mercury in it will expand for us to determine the temperature of that, for us to determine whatever temperature the thermometer is trying to give to us. So up to the 0 centimeter mark, let us assume that is the 0 centimeter mark, the 0 degrees Celsius mark, the 0 degrees Celsius mark, the volume of the mercury that is inside the bulb and the stem up to the 0 mark is, we'll take it as the initial volume, is 0.4 centimeter cube. Let's continue with the question. We are now also told that if the bore has an area of cross-section of 0.03 millimeters squared, the cross-sectional area of the bore is the narrow pathway through which the liquid will have to travel. If the bore has an area of 0.03 millimeters squared, what is the length of a degree on the scale? What is the length of a degree on the scale? What will be the length if the mercury is to expand to a point where the temperature will reach 1 degree Celsius from 0? If the mercury is going to expand to 1 degree Celsius, what will be the length? What will be the length of a degree on the scale of that temperature? What will be the length of a degree on the scale of that temperature? That is what we are asked to find. This question gives us the apparent cubic expansivity of mercury in glass to be 0.00015 per Kelvin. The apparent cubic expansivity of mercury in glass is 0.00015 per Kelvin. Apparent cubic expansivity. Of course, it's the apparent cubic expansivity that we are going to use because the glass thermometer itself will serve as a container. So we can use the apparent cubic expansivity to find the apparent change in volume that will occur to this mercury when heated through 1 degree Celsius, when it is exposed to a temperature increase of 1 degree Celsius, that is from 0 to 1. So we can now say that the apparent cubic expansivity must be 0.00015. It must be equal to the apparent change in volume. The apparent change in volume is what we don't know. The initial volume is 0.4. The change in temperature must be 1 to 0. We want to know what will happen to it, as in what is the expansion through which it will have to go to if the temperature is increased by 1. So quite simply, I can find that as my change in volume, my apparent change in volume must be, if I cross multiply, I will have 0.00015 multiplied by 0.4 multiplied by 1. So that should be 0.00015 multiplied by 0.4 multiplied by 1. We are going to have 0.00015 multiplied by 0.4 multiplied by 1, and the answer should be 6 times 10 raised to the power minus 5. So if we decide to heat this mercury in the bulb and stem up to the 0, if we decide to heat it just to increase its temperature by 1, we expect its volume to increase by 6 times 10 raised to the power minus 5. We are not done. So we will have to now, so that means the increase in the volume. We have a bulb that has a ball and there's mercury inside it up to the zero mark. By heating it for it to expand, we expect the mercury to expand to 1. In expanding to 1, what is the length? We've just calculated the change in volume that will be expected. The change in volume that will be expected is 6 times 10 raised to the power minus 5. And we know the area, the cross-sectional area of that stem to be 0.03 millimeters squared. The very first thing is, let me convert that area to centimeter squared because of the centimeter. I've been able to get the change in volume as centimeter cube. I will divide, if I'm changing from millimeter to centimeter, I will divide by 10 because I am squaring it. Anytime you are changing from millimeters to centimeter, you divide by 10. But if it is squared, you have to square all the other items. So if I want to change from millimeter squared to centimeter squared, I'll divide by 10 squared. And that should give us 0.0003 centimeter squared. Now, the change in volume that is expected from 0 to 1 is this. The cross-sectional area is 0.0003 centimeters. I want to find the length. What I will do is I will treat this volume separately, the change in volume separately. The formula for change in volume, since it is a cylinder of uniform cross-sectional area, the formula for the change in volume must be area multiplied by the length. So therefore, the length must be change in volume divided by area. And the change in volume divided by the area is 6 times 10 raised to the power minus 5 divided by the area. And my area, in that case, is 0.0003. That should give me a value that is equal to 0.2 centimeters. So I'm expecting, for a degree change in temperature, I'm expecting the liquid level to rise by 0.2 centimeters, because the volume is in centimeter cube, while the area is in centimeters squared. So if I divide that, I should have centimeters. With this, we have come to the end of this topic, and I hope you have been able to gain one or two informations that are essential to you passing an examination that is set on thermal expansion. So we'll meet the next time. Thank you very much.